Hi guys, hi. थोड़ा सा change किया setup. I have increased this distance now. I hope I'm visible, everybody. Hi, Surinder Singh. Hi, Neat Avenger. Sir, Neat Avenger is asking, sir, notes is there in the Telegram? I think notes are there in the Telegram. Notes are there in the Telegram. Did you guys find notes in the Telegram? I think notes are there in the Telegram. Neat Avenger, it should be there. Can you please check? Can you please check? I have shared the link to the folder, and in the Google Drive, in that folder all the notes are there, all of them are there. Okay, so it should be there. Yeah, today I'm in color after so many days. I removed that chroma key and everything, and I'm in color. Yeah, of course, yeah. Okay, so hi, smart book. Splendid achiever, everybody. Yeah. It was before, it used to be black and white cam. Now I'm in color. Okay, I because I'm teaching radiation today, I thought I should be in color. Mm-mm. Hi, Tamanna. Hi, Lavanya. Hi, smart book is also here. Nice slides. Oh, thank you so much. Thank you so much, guys. Thank you so much. Okay. All right, guys. So, let's talk about this. First of all, let's talk about. Hi, Jay Study. Hi, Sakshi. Hi, everybody. Okay. So, we need to talk about first the guy who commented the correct answer to the homework question. Okay, and who was that? Who was that? I believe it is Surinder Singh. Okay, Surinder Singh this has been the second time he has given the correct answer. Oh my God, Surinder is on fire. Like, not literally on fire, but like, as far as giving answers is concerned, Surinder is on fire. Oh. Neat Avenger, I have shared PDF notes. Neat Avenger, please check again. I've shared PDF notes. Guys, did you check the PDF notes, guys? Did you check the PDF notes? Yes. Can you tell me, guys, if you did check the PDF notes? If you did, then it would have been good. Okay, otherwise we are in trouble. I think PDF notes may there are annotations. Can you check? Anybody, can you check? Yeah, I have made a folder in the drive, smart book, exactly. And in that, if you check, there will be notes. Okay, there will be notes. Okay. So guys, what I had a situation like this. This was K1, this was K2, and this was K3, if you saw. Okay. And this one was maintained at a higher temperature, this one was maintained at a lower temperature. Okay, and what was happening is that the current going from here to here, the heat current going from here to here is the same as the heat current going from here to here. Okay, basically this heat current is the same as this heat current. Now, that is only possible, guys. If you see here, that is only possible if the equivalent resistance of these two is the same as the resistance of this. The equivalent resistance of K1 and K2 in series should be same as the equivalent resistance of K3. Okay, or I can write R1 plus R2 should be equal to R3. If the resistances are same, then the currents will be same. Okay, Mahendra Pal, no, you are not late. I'm just discussing the homework question. Okay, just the homework question. I had K1, K2, and K3. The resistances R1 plus R2 should be equal to R3. Okay, yes, annotations are also visible. Smart book, exactly. Okay. So, guys, from this, if I had to write R1, what will be R1? R1 will be nothing but L divided by K1 into A. Okay, and if I had to write R2 and R3, that will also be nothing but L divided by K2 into A and L divided by K3 into A. L divided by K2 into A and L divided by K3 into A. Are you guys following? Hi, spaceman. Hi. Okay. How do you wear on board? Okay, I don't know what you're asking, Manchester. Okay. Are NEET Avenger, please check. Yeah, please check again today, right now. Check, go and check. There are PDF notes there, NEET Avenger. It's there, handwritten part is there. If it's not there, then I will personally, come on. I don't know what I will do. But yeah, it's there, NEET Avenger. Okay, if you see this, guys, what happens here is and L will get cancelled out. A, and A will get cancelled out. I will have very simple equation. I will have very simple equation. 1 by K1 plus 1 by K2 is equal to 1 by K3, which gives me K3 is equal to K1 K2 upon K1 plus K2. Okay, so that will be the correct answer. NEET Avenger, please check one more time. Okay, it should be there. It should be there. How do you wear on board? Okay, I don't know, guys. How many, by the way, is there any 2020 person here? Is there anyone from 2020 here? Can you tell me what your result is? Ayush Hivale. Hi, Ayush. Hi. Welcome to today's class, guys. All right. So, now let's start today's lecture, which is about radiation. Okay, which is about radiation. This is the third mode of heat transfer. So guys, yesterday we talked about conduction. Okay, yesterday we talked about day before yesterday we talked about conduction. Then convection, you have to remember, is not part of the syllabus. Okay, you just have to remember that there are two types of convection: natural convection and forced convection. Other than that, convection is not part of the syllabus. Okay, then smart book, tomorrow there will not be any class. The next class will be on Tuesday. Okay, all right. Then we have a radiation, which is part of the syllabus, so that is what we will study today. Okay, Aditi Mishra, will there be regular classes from Monday onwards? Aditi Mishra, still not regular classes. We will see. Okay, I have had a lot of discussions about this, but we are no, there are a lot of variables. Okay, okay. Board कब आएगा? आयुष हिमालय board आएगा. Don't worry. Okay. Hi. By the way, Abhyuday. Hi. Okay. Menti session is there tomorrow? No, spaceman. No Menti session tomorrow. Okay. Tomorrow is just going to be a special session. I'm going to talk about one very famous Indian physicist. I don't know if you guys know his name. His name is Satyendranath Bose. Okay, so if you want to know more about him, he was very famous. He worked with Einstein. Okay, and he was super duper smart person. We'll talk about him tomorrow. Okay. All right. Azim Turkey, no Hindi, my friend, no Hindi. This is going to be English class. Okay. All right. So what exactly is a radiation? So radiation is basically, if you know about conduction and convection, you know that we need some material medium for heat transfer to conduction and convection. But in case of radiation, we do not need material medium. In case of radiation, no material medium required. Okay, that is the sole reason why Earth receives the heat energy from sun. Okay, because in between there is a whole lot of area where there is a vacuum, and we still get energy from the sun. Okay, even though there is huge distance and there is vacuum in between, we still get what? We still get the energy from the sun. This is through radiation. Now let's talk a little bit about radiation. Okay, whenever I say radiation, what I mean is an electromagnetic wave. Okay, whenever I say radiation, what I mean is electromagnetic wave. Okay, we will study about this electromagnetic wave more in class 12. Okay, there's a chapter called electromagnetic waves in your class 12. Okay, now this electromagnetic wave has very small building up to very small frequency, and it goes all the way up to very large frequency. Okay, this radiation has very small frequency and it goes up to very large frequency. Forget about this diagram here right now. Okay, and if you look at their wavelength, if you know, there is a relation between wavelength and frequency and speed of light. Speed of light is equal to frequency into wavelength. Okay, all these guys we will study next year. but you have to remember the smallest wavelength is even smaller than size of the atom. Okay, it's comparable to the radius of the nuclei, and the largest wavelength, which is the radio waves, its wavelength is comparable to size of big buildings. Okay, so we have electromagnetic radiations in various different wavelengths. The smallest possible wavelength is 10 power minus 12 meters. Okay, that's so small. It's comparable to size of the nucleus, and the largest wavelength is comparable to size of the buildings. Okay, this is the entire spectrum: gamma, X, ultraviolet, visible, infrared, microwave, radio. All this we will study next year. All this we will study next year. In between we have a small spectrum. In between we have a small spectrum which is visible to our eyes. In between we have a small spectrum which is visible to our eyes. Okay, now all these electromagnetic radiations, okay, all these electromagnetic radiations carry energy with themselves. Okay, so anytime an electromagnetic radiation goes from one point to another point, it carries energy with itself, and that is how heat gets transferred. That is how heat gets transferred. Now, in general, heat is mostly transferred through infrared radiation. Heat is mostly transferred through infrared radiations. Why is that? Because in general, if you look at any atom, let's say this is my hand, my fist is an atom. Okay, so whenever an atom gets heated, what it does is it starts vibrating. Okay, and when it starts vibrating, it gives out light energy. When it starts vibrating, it gives out light energy. Okay, so the light energy due to vibration of atoms is in general in infrared range. Okay, light energy due to vibration of atoms is in general infrared range. So most of the heat transfer generally takes place in the infrared range. Okay, I hope everybody understood. I hope everybody who is here, every one of you understood. Okay, Danush is asking, sir, you don't teach about ideal gas equation. Danush, I will teach about ideal gas equation in the next chapter. My friend, please be here. Okay, the next chapter is going to be KTG. So it's part of the thermal physics only. So KTG, I will talk about ideal gas equation. Do not worry. Okay, NEET Avenger. NEET Avenger, I thought NEET Avenger, this is not possible, my friend. In the PDF, there are supposed to be annotations. What are you saying? What are you saying? Okay, Ryan Fares, I'm so sorry, my friend. Today there is not going to be any class on kinematics. I wanted to take it, but I had to shift it to Monday. I'm so sorry. Okay, today we are going to have a class on. Today we are going to have a class on basic mathematics, that is differentiation. Okay, no. Okay, kinematics will not be there today, Ryan Faris. Sorry. Okay, so let's talk about radiation and how radiation interacts with material. Okay, so let's say I have any body. Okay, let's say I have any body. Okay, let's say this is a body here, and some radiation is incident on it. Okay, some radiation is incident on it, or basically some energy is incident on it. Let's call this energy as delta qi. Okay, what is delta qi? By the way, let's not call it delta qi, let's just call it qi. Okay, the energy is incident on it. And what is qi? Qi is basically energy incident on the body. Energy incident on the body. Okay, now if you look at this incident energy, when it falls on the body, this body has basically three different choices about what to do with this energy. Okay, this body has three different choices about what to do with this body. Okay, with this energy. Okay, what it can do is it can reflect this energy back. Okay, it can reflect this energy back. Okay, where QR becomes the energy reflected. Okay, it can transmit the energy. Okay, so if you have something like what should we call it, a transparent object, what will happen is when energy is incident, that energy will go through the body. So it can transmit this energy. QT is energy transmitted. Okay. And finally what it can do is it can absorb this energy. Okay. The one last choice that it has is that it can just absorb this energy. You just absorb it. QA. QA is the absorbed energy absorbed. Alright, guys, I hope everybody understood so far. So, these are the three choices that any material has when energy is incident on it. Okay, am I lagging? Am I what should I call it? Am I buffering? Am I buffering? SAS Creations is saying I'm buffering. Okay, I don't know. Okay, so now what happens is, guys, like if when all of this is happening, there is still something called law of conservation of energy. Okay, if you look at most materials, they always do a combination of all three. Okay, they always do a combination of all three. So if you look, let's say, like a shiny mirror, so on a shiny mirror what happens is whatever energy is incident, it reflects back almost 90% of it, but there is still like a small amount that it will absorb. Okay, or any other material, what if you see like a glass slab will transmit most of the energy which is going through it, but it will still absorb a little bit of energy. Okay, so most materials will do a combination of QRQA and QT. They will absorb a little bit, they will reflect a little bit, they will transmit a little bit, but always there will be a law which will be that will be followed, and that is loco energy. Okay, what does loco energy stand for? That stands for law of conservation of energy. Okay, this will always be followed. Okay, and what this means, guys, what this means is that the total energy incident will always be equal to the total energy reflected plus the energy absorbed plus the energy transmitted. Okay, the energy reflected plus absorbed plus transmitted. Okay, I hope everybody understood. Okay, these are the three things that are happening, and their sum will always be equal to this. Is everybody okay? Everybody's okay. Everybody's okay. These are what we called the uh, these are the three things that can happen when energy is incident on a body. Okay. Now what happens, guys? Now, this is where Nikhil Sharma, you are late by a little bit. Okay. Spaceman is asking, sir, what is the difference between reflected and transmitted? Okay, spaceman, this is a very khatana question. Okay, so let me make you understand what is the difference between reflected and transmitted. Okay, what exactly is reflected and transmitted? Spaceman, if you take a glass slab, okay, and give energy, radiate energy on the glass slab, most of that energy will just go out of that glass slab. Okay, if energy is radiated on the glass slab, it will just pass through. But if you have a mirror instead, okay, and in this case, if you incident energy on this mirror, what will happen, that energy will get reflected. So this is a transmission. Okay, glass slab does it best, and this is a reflection, mirror does it best. Okay, but that doesn't matter that other things are not reflecting energy. Okay, for example, if you look at this bottle, guys, can you see this bottle? Can you see this bottle? So if you see, this bottle is a little bit transparent. This bottle is a little bit transparent. Okay, you can see my eyes through this bottle. So what you can say is that some part of the energy which is incident on this bottle, some part of this energy which is incident on this bottle will pass through. Okay, somebody is asking what is loco energy. Loco energy is the law of conservation of energy. Okay, some part of energy incident on this will pass through. Okay, and some part of energy incident on it will also get absorbed. In this case, this is red colored body, so it's probably absorbing all the colors except reds. Okay, so when light is passing, let's say white light falls on it, on the other end, what comes out? All the only red colors come up. So what is it absorbing? It's absorbing all the colors except red. Okay, and it's also reflecting a little bit of light, because you can see it's shining a little bit. Okay, it's shining a little bit. Its shininess will increase if I open the window, okay, the curtain, and that means it's also reflecting energy. So it's doing all these three things, guys. Okay, and the total sum will always be equal to the energy incident, because law of conservation of energy. Now here I define three different factors. How many factors do I define? How many factors do I define, guys? Tell me in the chat if you know how many factors will I define. I'm defining three different factors. Okay, I define the first factor as A. Okay, this A is called absorptivity. Absorptivity. Okay, A is also called coefficient of absorption. Okay, what is A? What is A? A is the ratio of energy absorbed divided by energy incident. Okay, A is the ratio of energy absorbed divided by energy incident. This is very simple to understand. Let's say if I incident about 100 joules of energy, okay, and out of that it absorbs 25 joules of energy, then A will be 25 by 100 or 1 by 4. Or you can say that this body absorbs 1/4 of all the energy incident on it. Okay, all right. Next is the next coefficient that I will define is R. R is called reflectivity. R is called reflectivity. Okay, and it is also called coefficient of reflection. It is also called coefficient of reflection. And what is R? Once again, it's very easy to understand, guys. What is R? What is R? What is R? R is nothing but the total energy reflected divided by the total energy incident. Total energy reflected divided by the total energy incident. I hope you guys are following. If you are following, please give me a thumbs up. Okay. Finally, we also define something called T. T is called what? T is called what? T is called transmittivity. Transmittivity, or it's also called coefficient of transmission. It's also called coefficient of transmission. Okay, now guys, if I ask you what its value, it's QT by QI. Okay, QT by QI. Now, if I ask you that I have a glass slab, okay, and this is like a perfectly transparent glass slab. Okay, this is like a perfectly transparent glass slab. So in this case, if I ask you what is the T value for this glass slab, can you tell me what will be the value of T for this glass slab? Tell me in the chat, guys. Tell me in the chat what will be its T value. How much will be its T value? If it's a perfectly transparent glass slab, exactly, Surinder Singh is correct and Spaceman is also correct. Its T value will be 1. Okay, why will its T value will be 1? Because whatever energy is incident will be transmitted. Okay, because this is a perfectly transparent glass slab. I hope everybody understood. Yeah, Dhanush also understood. Whoa is also here, and he also understood. Very good, very good. Similarly, let's say I have a mirror, and this mirror is a perfect mirror. Okay, perfectly reflecting mirror. Okay, so in this case, what will be the R value for this mirror? What will be the R value for this mirror? Can anybody tell me? Thank you so much, SK Mishra. Thank you so much. What will be the R value for this mirror? Everybody knows. Tell me. Correct. Surinder Singh is again correct, and SK Mishra, Spaceman, whoa. Dhanush, all of you are correct. It will still be 1. Very good. Now, similarly, guys, I can also have something called, a perfect a perfect black body. I can have something called a perfect black body. Okay, what exactly is the property of a perfect black body, guys? What exactly is the perfect black body? Okay, because whenever energy is incident on it, it just absorbs all of that energy. Whatever energy is incident on it, it will just absorb all of that energy. And for this, A will be equal to what? 1. Okay, this is called a perfectly black body. Okay, or it is also called an ideal black body. Okay, Dr. Ansab is wanting me to increase the class timings. Dr. Ansab, I'm working on that. I'm working on that. Do not worry, I will try to increase my class timings. Okay, definitely, definitely, definitely. Okay. All right. I hope everybody understood, guys. I hope everybody understood. Really, really hope everybody understood. Okay, now guys, coming back to this once again. Okay, coming back to this once again. Let's go back to this. If you look at this slide, ज़्यादा नीचे नहीं, ज़्यादा नीचे नहीं. I भागता बहुत है. हाँ. So if you look back at this slide, guys, if I do the sum of all these three factors, if I do the sum of all these three factors, what are the three factors that I'm going to do the sum of? I'm going to do the sum of A plus R plus T. Then can you guys tell me how much will that sum be? Can you guys tell me how much will that sum be? Okay. Avinash, black hole is a little bit different. We will talk about black hole in some time. Okay, black hole is not a perfectly black body. We'll talk about it. Okay. Mm-mm. Can anybody tell me what will be the sum of all these three? What will be the sum of all these three? The sum of all these three will be equal to 1. Very good, guys. That will be equal to 1. Okay. Why will that be equal to 1? Because if I add, you have to remember because QA plus QR uh, 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 QA plus QR plus QT is equal to QI. Okay, the sum of all the energies is equal to the energy incident. I hope everybody understood. I really hope everybody. No, 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 smart book. No, 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 no. It will not be three smart book. It will be one. Okay. Now, what that means is, guys, what that means is that for this body, if T is equal to 1, then that means that for this body, A will be equal to 0 and R will be equal to 0. Okay. Similarly, for this body, if R is equal to 1, then for this body, A will be equal to 0 and T will be equal to 0. Okay, then also at the same time, if I have a perfect black body, and everybody has to pay very close attention to perfect black body because we are going to study that mainly in this chapter. For a perfect black body, guys, if A is equal to 1, then R will be equal to 0 and T will be equal to 0. It will only absorb energy, it will not reflect, it will not transmit. Okay, I hope everybody understood. I really hope everybody understood. Okay, based on this, guys, let me give you a very simple question. I think everybody should be able to solve. I have coefficient of absorption of a body which is 0.68. Okay, when 100 calories of heat is incident on this body, 27 calories are reflected. You have to find the coefficient of transmission. It's not a hard question, guys. I think everybody should be able to solve. I will give you 2 minutes to solve. Tell me the answer in the chat. Okay, tell me the answer in the chat. Everybody should be able to solve. Hi, hi, Dreams Kidnapper. Hi. Everybody should be able to solve, guys. Tell me what will be the coefficient of absorption. Sorry, the coefficient of transmission. It's not hard. It's easy. It's easy. Neat Avenger, my friend, I am so sorry if you're not getting the notes. You should be able to get the notes, okay? You should be able to. Neat Avenger, you will. Please check. It should be there. It should be there. Surrender is saying, hmm. Surrender, A is not asked in the question, Surrender. Something else is asked. Please tell me what the answer should be, guys. I will give you 1 minute. Mm-mm-mm. I will give you 1 minute. I will give you 1 minute. Hi Akash Dev, welcome to Momentum with Vedantu. Everybody, tell me the answer. Tell me the answer. See, how will we do this? Here, A is already given as 0.68. Okay, and QR is given as 27 calories, while QI is given as 100 calories. Okay, so from this I can calculate R, which will be 27 divided by 100, which will be 0.27. So now if I want to calculate T, how do I calculate T, guys? Or it's super hard, no? It's super duper hard. How to calculate? Oh no 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 no! I am so stuck. What equation will I use? A plus R plus T is equal to 1. Okay, substituting the values, I will get 0.68 plus 0.27. Okay, plus T is equal to 1, which gives me T is equal to 1 minus 0.68 minus 0.27. Guys, my maths is not very good. My maths is not very good. Can you please tell me how much will this be? Will it be 0.05? Will it be 0.05? Yes, it will be 0.05. Very good. Spaceman is correct. Surinder is correct. The spaceman is again correct. And Ram Babu Rakoti is also correct. Very good. Dreams Kidnapper ने थोड़ा सा गलती किया, but ठीक है. Dhanush 2022 also correct. Very good, very good, very good. Okay, let me give you one more question, guys. Let me give you, see, these are easy questions. I think you should be able to do one more question. For an athermanous body, okay, don't worry about the name. Basically, this is a body which has T is equal to 0. Okay, for an athermanous body, the coefficient of absorption is this. Then find the quantities of heat absorbed and reflected. Okay. Yes, Ryan Faris, I will. Ryan Faris, definitely, my friend, definitely, definitely, definitely. Okay. Mm-mm. Everybody, tell me. For this metal plate, the coefficient of absorption is 0.65. Then, if 500 kilocalories is incident, then find the heat absorbed and the heat reflected. Can you guys tell me? Can you guys tell me? La 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 la. Can you guys tell me? You should be able to give me the answer in the comment section, in the chat section. Very good, very good. Surinder Singh is always there with the correct answer. How to do this, guys? Once again, if you see, A is given as 0.65, and because this is an A thermalus body, T is equal to 0. R we can easily calculate. How will we calculate? I can write A plus R plus T is equal to 1. Okay, R is equal to 1, which gives me 0.65 plus R plus 0 is equal to 1, which gives me R is equal to 0.35. Okay, now I can write A is equal to heat absorbed upon heat incident, okay, which gives me 0.65 is equal to heat absorbed divided by 500, which gives me heat absorbed is equal to 500 into 0.65. Okay, I don't know if you guys know how to do this math. This will be 325 calories. Okay, not calories, 325 calories. Okay, or kilocalories. Similarly, I can use R is equal to QR divided by QI, or 0.35 is equal to QR divided by QI, which gives me QR is equal to 0.35 into 500, which is nothing but 175 kcal. Okay, or 175 kilocalories. I hope everybody understood. Hi Avinash, absorbed is not 500. Avinash, incident is 500. Okay, where is your school? Spaceman, my school is not, it's in Gujarat actually. Okay, Akash Dev, I am from Gujarat state. I am from Gujarat state. I hope everybody understood. I can see your chats, guys. You see, I can see your chats here. Okay, so I can see your chats here. So, yeah, I think you knew I see your chats. Okay, but anyways, I have to see your chats on the phone. Yeah, yeah. Okay, Akash Dev, I am on this. Okay, क्या बोलते हैं? I'm from Gujarat. Yeah. Alright. Now, let's talk about black body radiation. But before we talk about black body radiation, we need to talk about an ideal black body. So now, guys, the thing is now there are no surfaces on Earth which can be considered ideal black body. Okay, there are no surfaces. There are no surfaces on Earth. Okay, which are perfectly black, perfectly black. Okay, what that means is there is no surface available which absorbs 100% of the energy, 100% of the energy. Okay, now there are a few substances available to us, there are a few substances available to us which are very very black. Okay, and which do absorb approximately, if 100 joules of energy is incident, they only reflect zero point 0.2 joules of energy and they absorb 99.8 joules of energy. Okay, so there are bodies which are what we can call them nearly perfect black body. Okay, nearly black. Okay, but there are no such thing which absorbs 100% of the energy. So what we have done is we have experimentally created a body which acts like a perfect black body, which is, it's not a perfect black body, but which can act like a perfect black body, and that is called, guys, that is called Fairy's black body. That is called Fairy's black body. Okay, taste the thunder. Thank you, Ahir Aaditya. Thank you so much. Okay. Okay, so what exactly is Fairy's black body? What exactly is Fairy's black body, guys? If energy is incident on this body, the insides of this body, okay, is made up of that almost perfectly black body. Okay, the insides is made up of that almost perfectly black body. Okay, so what happens is that when energy is incident, 99% of it is absorbed and then 0.2% is reflected. Then once again here, 99.8% of that 0.2% is absorbed and the 0.2% of 0.2% is reflected. Here also for whatever energy is incident, 99% of that energy is absorbed and then the remaining is incident. So basically after 3-4 reflections, the energy that gets reflected becomes very very small, and basically you can consider this as an ideal black body, can be considered as ideal black, as ideal black. Okay, I hope everybody understood. I really hope everybody understood. Now, what exactly is black body radiation? And this is where, guys, now the radiation part of our chapter starts. Okay, this is where the radiation part of our chapter starts. Okay, what exactly is black body radiation? So guys, what happens is that if I take a black body, a Fairy's black body like this, okay, and I heat it up to a very high temperature. I heat it up to a very high temperature. Okay, I heated it up to a very high temperature. Okay, let's say the 1000 Kelvin, 2000 Kelvin, something like this. So what happens is now that the black surface inside starts radiating. Okay, have you ever seen an iron block? Have you ever seen an iron block? If I heat that iron block to a very high temperature, it starts glowing, right? It starts glowing. Have you seen that? Have you ever seen that in real life? The same thing will also happen to this black body. If I heat it to a very large temperature, guys, it will start radiating heat. It will start it will start glowing. Okay, and I will only see that glowing light coming out from this small hole. Okay, because we will be somewhere here and we will only be able to see that light coming out from this small hole. Okay, so what happens is when we heat this to very high temperature, we can see light coming out of from this small hole. And what we do is we analyze this light. We analyze this light. Okay, now this is the light emitted by a black body, so we call this a black body radiation. Okay, so we analyze this light, and this light is called a black body radiation. This the radiation, the radi one second. The radiation emitted by this body is called black body radiation. Now, when we analyze this, guys, when we analyze this radiation coming out from this perfect black body at very high temperature, what we saw was a graph like this. What we saw was a graph like this. Okay, now let me make this graph bigger so that you can see what is happening here. You can see what is happening here. What we saw in this graph, guys, is this, that if my temperature is low, if my temperature is low, then the energy emitted looks something like this. Okay, this graph, by the way, is between what and what? This graph is between energy emitted and wavelength of radiation. Energy emitted and wavelength of radiation. So, of course, if my temperature is low, then the light emitted will also be low. Everybody understands that. And the wavelength and everything, the graph will correspondingly looks something like this. Now, when I increase the temperature, the first thing I see, guys, is that the amount of energy radiated increases. The amount of energy radiated increases for all wavelengths. For all wavelengths, the amount of energy radiated increases. Okay, so for 10 micrometers, the energy radiated increase. For 5 micrometers, the energy radiated increase. For 15 micrometers, the energy for all wavelengths, basically the energy radiated increase. So very good, very good, very good. I understand that. Everybody understands. Now, if I increase the temperature even further, once again the energy radiated at all wavelengths, or मेरा vacuum का body खत्म हो गया. The energy radiated at all temperature increase at all wavelengths increases. Okay, this is higher wavelengths, this is lower wavelengths. Okay, so in general it falls in between. The graph looks something like this. Okay, this material, Josh is asking, sir, what is it made up of? Josh, you have to understand it's an ideal black body. Okay, it's like the blackest surface you can assume. Okay, so for if you look at the blackest surface, okay, that surface is called an ideal black body, and if you heat it to high temperature, it will start radiating. And I'm looking at that radiation in this graph. Okay, I'm looking at that radiation in this graph. Okay, I hope everybody understood. Did you guys understand? Did you guys understand? If you can, if you did, give me the thumbs up. Okay. This is, by the way, this graph is all experimental. Okay, this graph is all experimental. This is experimental analysis. I saw all of this. I did calculations. I drew the graph after a lot of experimentation. Okay. I hope everybody understood. I hope everybody understood. Now, what I saw is that when I heat up a body, okay, let's say if I heat up this cup and I heat it up to a very high temperature, it will emit a radiation, but it will not just emit one color of radiation. It will emit all different colors of radiation. Okay, you can understand that by looking at this wavelength. See, it is emitting energy. It is emitting energy at all different wavelengths. It's emitting energy at 5 micrometer, at 10 micrometer, at 15 micrometer, at 20 micrometer, at 25 micrometer. It's emitting energy at all different wavelengths. Okay, this is called continuous emission. क्या बोलते हैं इसको हम लोग? Continuous emission. Okay, but there is always this peak which happens at a certain wavelength. There is always this peak which happens at a certain wavelength. So basically, for that wavelength, the energy emitted is maximum. Okay, so if you look at the 300 Kelvin graph, that peak happens somewhere here. If you look at the 400 Kelvin graph, the peak happens somewhere here. Okay, and if you go further to 500 Kelvin graph, the peak happens for some other wavelength. The peak happens for some other wavelength. Do you guys understand? Do you guys understand so far? What is happening is experimentally I saw something. Experimentally I saw something. What did I see experimentally? That that this peak wavelength, I will call it lambda m, the wavelength at which peak energy is emitted, maximum energy is emitted, is inversely proportional to the temperature. As I am increasing the temperature, the peak value keeps on decreasing. Do you see that, guys? Do you see that? This is all, by the way, what? This is all, by the way, experimental. If you can see that, please give me a thumbs up. If you increase the temperature, the wavelength at which maximum emission occurs is decreasing. The wavelength at which maximum emission occurs is decreasing. Okay. Now, if I want to remove this proportionality, what do I add? I add a constant. Okay, this constant is called B. This constant is called B, and B is Wien's constant. Okay, it's called Wien's constant or Wien's constant. Okay, and it has a fixed value. B is basically equal to 0.0029. 0.0029, what is that going to be? Yeah, meter Kelvin. 0.0029 meter Kelvin. Okay, this is a constant that Wien got experimentally. Okay, he did a lot of experiment, and that is when he got this constant. Does everybody understand so far? Everybody understand so far? Okay, Avinash is asking, sir, if you increase the temperature more than 500 Kelvin, then what will happen? Avinash, if you increase the temperature even further, then your graph will look something like this. It will again go up. Okay, it will again go up to a very big height, and then it will come down. Okay, but because the temperature is higher, then in that case this will again decrease. Do you understand? Do you understand? I hope everybody understood. Okay, spaceman sir, when will you plan the week timetable, sir? Array spaceman, I will very very soon. Spaceman, I will very very soon. Okay, I hope everybody is following so far. This is just all experimental that we saw. Okay, this, by the way, this is called Wien's displacement law. This is called Wien's displacement law. That the spectral radiance, okay, spectral radiance is just the energy emitted, is peak. It is maximum at a certain wavelength lambda m. It is maximum at a certain wavelength lambda m. Okay, and this lambda m is given by lambda m into t is equal to constant, and this constant is called B, which is Wien's constant 0.0029 meter Kelvin. Okay. I hope everybody understood. I hope everybody understood. Okay, Atharva Sharma, the Vedantu's Telegram group is available in the comment section, in the description of this video. You can see that. Okay, not Atharva Sharma, Abhyuday. Okay, it's there, it's there, it's there. Oh, Dreams Kidnapper also studied it in chemistry in class 11. Oh, this is also class 11th only, Dreams Kidnapper. But yeah, I explained it again because I don't know. I just explained it again. Okay, then let's talk about emissivity, guys. Let's talk about emissivity. What exactly what exactly? Oi, Ajay Kritik, I did not score good marks in AIMS, okay? I did not score good marks in AIMS. Ajay, that was my students who scored good marks in AIMS, not me, not me. Okay, I only gave JEE advanced, yeah. Okay. So, the emissivity of a surface is the effectiveness in which it emits thermal radiation. So now guys, let's talk about emissivity for a minute. Okay, let's talk about emissivity for a minute. So here you have to remember a certain very, very important fact. Okay, you have to remember a very important fact, which is that absorbers, good absorbers are also good emitters. Good absorbers are also good emitters. Okay, what do I mean by that, guys? What do I mean by that? So let's say I take a china plate like this. Okay, I take two different plates. Okay, two different plates is made up of that china wo jo जिससे ये जो cup जिससे बना है ना वैसे two different plates. Okay, but one of this plate is made up of black color. Okay, and the other one is made up of white color. Okay, now guys, if I ask you which of these two will be a better absorber? Can you tell me which of these two will be a better absorber? Which of these two will be a better absorber? Tell me. In the chat, tell me in the chat, which of these is the better absorber? Very quickly tell me, guys, very quickly tell me. The black one, yeah, exactly. The black one is a better absorber. Okay, but if I heat both of them, okay, if I heat both to 1000 Kelvin, okay, then in that case, what happens is both of them will start glowing. Both of them will start glowing. Okay, this one will also start emitting light, and this one will also start emitting light. Okay, now here if I ask you, which one will glow brighter? Can you tell me which one will glow brighter? Can you tell me which one will glow brighter? Which one will glow brighter at 1000 Kelvin? Tell me. The black one or the white one? The black one or the white one? Which one will glow brighter at 1000 Kelvin? Everybody tell me. Okay, Neat Avenger is saying, okay, sir. Spaceman is saying white. Justice is saying white. Swati Live to Serve is also saying white. See, guys, this is where you have to understand. This is where you have to remember this rule. This is a rule. Okay, what is the rule? Good absorbers are also good emitters. Okay, good absorbers are also good emitters. What this means is that this will absorb more energy, black will absorb more energy, but also at the same time black plate will be brighter at 1000 Kelvin. It will glow brighter compared to a white plate. It will glow brighter compared to a white plate. Okay, you have to understand that anything which is black is also very good at emitting it back. Good things, atoms which absorb very well are also going to be the same atoms which emit very well. Okay, I hope everybody understood. I hope everybody understood. So if I ask you that which type of objects are best emitter, then what are best emitters? Okay, what are best emitters? The best emitters will be what are best emitters? Okay, so the best emitters will be equal to perfect black body. Perfect black perfect black body are super good at absorption, so they are also going to be super good at emission. They are going to emit maximum brightness if you take them to very high temperature. Okay, super perfect black bodies are going to be the best emitters. Okay, now based on this, guys, we come to the next definition. Okay, what is the next definition? It is called emissivity. Okay, emissivity is written as E. Okay, emissivity is written as E. Okay, now what exactly is emissivity, guys? What exactly is emissivity? So let's take two different bodies. Okay, let's take a perfectly black body, keep it at temperature T. Okay, high temperature T. Okay, and let's take a normal body. Okay, some random body, and also keep it at random temperature T. Okay, now if you look at the energy emitted by both, if you look at the energy emitted by both, which will emit higher energy, the perfect black body will emit higher energy. Okay, all right, this is some random body, some body. Okay, but what happens is, guys, what happens is that if what is emissivity, guys? Emissivity is basically how good this body is compared to the black body. Emissivity is defined as what? It is basically the energy emitted by this body, energy emitted by this right wala body, by this body, okay, divided by energy emitted by perfect black body, energy emitted by perfect black body. Okay, if you have a perfect black body, it's going to emit the maximum amount of energy. This some body at the same temperature will emit little bit less energy. So the ratio of these two is called emissivity. Okay, now either Abhyuday is asking us, sir, why does black body absorb and emit more? First of all, Abhyuday, it's black because it absorbs more, and because it has the ability to absorb more. When the atom vibrates, okay, it will also emit more. Okay, it goes hand in hand. Okay, it goes hand in hand. It's basically, yeah. So E is called emissivity. You can also call it coefficient of emissivity. Okay, will you complete the whole physics 11 class 11 chapter before December? Yes, smart book plan तो यही है, by December or at least mid January, definitely. Okay, all right. I hope everybody understood so far. I really hope everybody understood so far. Now, next we have something called, now guys, this is where things are going to get a little bit mathematical. So please stay with me. Okay, stay with me. Do not go away. Stay with me. Do not go away. We have something called Stefan-Boltzmann law. Okay, we have something called Stefan-Boltzmann law, and this law is also experimental. This law is also experimental. Okay, so let me tell you what exactly is this Stefan-Boltzmann law. Okay, so this is Stefan-Boltzmann law. Okay, let me tell you what exactly this is. So let's say I take an ideal black body. Let's say I take an ideal black body. Okay, this is a black body. And what I do is I heat it up to a very high temperature. I heat it up to a very high temperature. Okay, so what will happen? This body will start glowing. This body will start glowing and it will start giving out energy. Okay, it will start glowing and it will start radiating energy. Okay, let's say the amount of energy it radiated, let's say the amount of energy it radiates is QE. QE is basically the energy radiated. Okay, so now the first thing that we can, if we, this Stephen and Boltzmann, what they did was they did a lot of experimentation. Okay, and what they found using experimentation, guys, is this. First of all, the amount of energy emitted, okay, the total amount of energy radiated, okay, is directly proportional to time. Now, this is very, very obvious. This is very, very obvious. Okay, what that means is, like, if you look at it for 2 minutes, it will emit some radiation. If you look at it for 4 minutes, it will emit double that radiation. The more time you will look at this body, the more it will emit the radiation. The more time it has, the more energy it will radiate. So that is very understandable. I think everybody understands. Correct? The more time this body will have, the more energy it will radiate. Very good. The next is this QE, the energy radiated, is also proportional to the surface area of it. This is also proportional to the surface area of this body. Okay, what that means is if you increase the area of the surface, more number of molecules will be able to throw out energy, and therefore more energy will come out. I hope everybody understood. Okay, one last thing that they found is that this energy radiated, and this last thing was the one that stumped everybody, and this was all experimental, but they found this, that this energy radiated is proportional to T raised to the power 4. Here T is the temperature. Okay, basically, if you double the temperature, guys, the energy radiated becomes 4 times. If you double the temperature, guys, the energy radiated becomes 4 times. Okay, now if you combine all of that, you get what? The energy radiated is proportional to AT raised to the power 4 into T. Okay, now if I want to remove the proportionality, what do I have to add, guys? If I want to remove the proportionality, what do I have to add? What do I have to add? I have to add a constant. What do I have to add? I have to add a constant. This constant is called sigma. Okay, this constant is called sigma, and sigma is basically called Stephen's constant. Okay, this is called Stephen or Stefan-Boltzmann constant. Okay, and its value is very easy to remember. This is all experimental and they calculated its value and it's not very hard to remember. Its value is 5678. Okay, or 5.67 into 10 power minus 8. 5.67 into 10 power minus 8. Okay, watt per meter square Kelvin raised to the power 4. Watt per meter square Kelvin raised to the power 4. Hi, Bhavna. Okay, I hope everybody understood. Really hope everybody understood. I really hope everybody understood. Okay, this is what we call Stefan-Boltzmann law. This is what we call Stefan-Boltzmann law. Okay, now Stefan and Boltzmann, they defined another quantity here. Okay, they defined another quantity here. What did they define? What did they define? They defined another quantity called emissive power. They defined another quantity called emissive power. Okay, what exactly is emissive power, guys? Emissive power, they defined it as basically energy radiated, energy radiated per unit area per unit time. Energy radiated per unit area per unit time. Okay, so if you try to substitute all the values, energy radiated is basically what, guys? Energy radiated is nothing but QE. Okay, area is equal to what? Area is A and time is T. So this is just QE divided by A into T. If I substitute the value of energy radiated here, this will be sigma AT raised to the power 4T divided by AT. What will remain, guys? What will remain? If you check this, what will remain? This A and T will get cancelled out. This A and T will get cancelled out. And what will remain is just this. Okay, this is called Stephen's law. This entire thing is called Stefan-Boltzmann law or Stephen's law. Do you guys understand? Do you guys understand? Do you understand? Do you understand? I hope everybody understands. I hope everybody understand. Guys, are you with me? Are you still with me? Yes? Okay. Hi. Hey, take a look at me. Take a look at me. I hope you guys are with me. So today, guys, we studied a lot. Today we studied a lot. Okay. But I was not able to finish this chapter because it's a big chapter. So I will continue this on Tuesday once again. Okay. One last thing before I go, I want to teach you. One last thing before I go, I want to teach you that, and that is this. Okay, what is it exactly that I want to teach you? Stephen-Boltzmann law is for what? It is for ideal black body. Okay, Stephen-Boltzmann law is for ideal black body. But instead of ideal black body, what if I had some random body? Okay, what if instead of ideal black body I had some random body? Then for that random body, guys, what I will define is E. What I will define is E. And what is E, by the way? What is E? E is emissivity. Okay, for that body, what I will define is E, and E is emissivity. Okay, now you have to remember this, guys. You have to remember this, that if I have emissivity E is basically defined as energy radiated by this random body, energy radiated by body. Okay, energy radiated by body divided by energy radiated by black body. Energy radiated by black body. Black body. Okay, or I can write E as nothing but energy radiated by this random body, what we are talking about here, what we are somebody, what we are talking about here. Okay, divided by divided by EB, where EB is emissive power of perfectly black body, of perfectly black body. Okay, so this is the real definition of black body. This is the real definition of emissivity. Okay, what is emissivity? It is basically emissive power of a normal body divided by emissive power of a perfectly black body. From this, if E is equal to E by EB, I can write E is equal to E into EB. So for a normal body, emissive power is equal to its emissivity into emissive power of the black. Now, the Stefan-Boltzmann law, guys, is given for a black body. So here, actually, I am supposed to put a B here, because I'm talking about a normal black body, which means that if I talk about any general body, here the emissive power will be equal to E into sigma into T raised to the power 4. If I'm talking about just somebody, then I have to multiply it by a factor of E, because the formula that Stefan and Boltzmann got was only for black body. For any other body, I have to multiply it by a factor E. Okay, I hope everybody understood. I really hope everybody understood. Okay, so based on this, guys, I will give you a homework question for today. And this is the homework question. This is the homework question. This is the homework question. A body of a surface area 10 centimeters square and temperature this emits 300 joules per minute. Find its emissivity. You will have to remember, guys, that for a body which is like this, not a perfectly black body, the amount of heat emitted will be equal to E A sigma T raised to the power 4 into T. You have to use this formula here. To get the correct answer. Okay, spaceman, I will complete ray optics very soon. I have started refraction only already. It was supposed to be completed in 14 lectures. I will definitely complete it within 14 lectures. Do not worry. Okay, all right. I hope everybody understood, guys. I really hope everybody understood. And that is it for today, guys. That is it. I don't have anything else to teach you. Please solve this question and write down the answer in the comment section. Okay. I will continue this class again on Tuesday, where we will finish radiation. Okay. Comment the answer. All right, guys. Okay. Now, before we go, let's take a minute and talk about Vedantu's NEET and JEE platform. Guys, you guys are saying that I'm not teaching this and I'm not teaching that, and I understand this is YouTube. We have limited period of time here. If you want everything in detail, okay, all the detailed notes, all the detailed examples, and this and that, then you should definitely check out Vedantu's JEE and NEET platform. Okay, here we have you. If you take the pro subscription at Vedantu, you are not limited to 1 or 2 classes a day. You can watch as many classes you want in a day. Okay, what is so special about Vedantu's platform, guys? When you take the pro subscription, you get full access to all the live courses which will be taught in both the languages, English and Hindi. You get to choose which language in which you want to study, where you will have class teachers in the class who will solve all of your doubts. Okay, and it will be taught by India's best teachers, all of them having 5+ years of experience. And let's say you missed a few topics. Okay, let's say you were sick that day and you were like, I don't want to take class today, and you just didn't see the class. And then you are later, you're like, oh, now I want to study that topic. What do I do? What do I do? So on Vedantu platform, guys, you will also find micro courses. Okay, you'll also find micro courses. These micro courses are topic wise. Okay, these micro courses are topic wise, and you can just take up that micro course for free to clear your previous doubts or to study the topic that you have missed. Okay, and when you take the pro subscription, you get unlimited access to these micro courses. Okay, these micro courses, by the way, live lectures. You can take up micro courses for live lectures. These are live as well as recorded lectures, but also live lectures, and you can take that up for free if you have pro subscription. Okay, and what do you have to do if you want pro subscription, guys? You have to go to vdnt.in/ytpro. When you go to vdnt.in/ytpro, use my coupon code AAPPRO to get additional 15% discount. You want to see what the prices are? Well, per month prices are 6,999, and for 12 months the prices are 31,800. But if you try to calculate it per day, these are less than a movie ticket. Okay, so if you want to prepare very very well, you should definitely check it out. And finally, I want to talk about last time. So नहीं ये तो बात कर ली ना हम लोगों ने. हाँ, सुरेंद्र सिंह, it was the guy who gave the correct answer last time. Okay, so superb, Surinder, superb. I will see you guys in the next class. Have a nice day, everybody, and see you. Okay, ciao, bye.